Okay, so for this lecture, we'll talk about the series resonant converters, or specifically the series resonant inverters. We have H bridge here, and you'll find that the resonant component or the resonant tank will be on the load, on the output of this inverter. Okay, not on the switch itself, not on the input side, but on the load side. So that's why we call this load resonant converter. And because the capacitor and the inductor are in series with the resistive load, so this is a series resonant converter or series resonant inverters. This H bridge can produce what? Can produce a square wave, and the current on the output can be either positive or negative. If we manage to get the current in phase with the voltage, this is a resistive load. So here, if we have no capacitor inductor here, so definitely the current will be in phase with the voltage. But if we have inductance or capacitance, so we expect that the current will be either delayed or the voltage will be delayed, right? Either one of them. But in the case of the resonant circuit, if we manage to get the capacitor and the inductor to be tuned at the resonant frequency, so we have two components here, the value of the capacitor and the inductor, and also the value of the frequency. So these three elements, or these two elements, the component value and the frequency value, if they are tuned at the resonant frequency, then we will be able to get what? The current and the voltage again in phase. Okay, even if we have capacitor and inductor at this moment. Let's look at the mode of operations for this inverter. We said either the voltage can be positive or negative, square wave. The current also can be either positive or negative. If the current is positive, the voltage is positive. This means the current is flowing through the switches. If the voltage is negative, the current is negative, then also again the current will be flowing inside the transistors. Okay, the opposite, the current will be flowing inside the diodes, right? So let's look at the mode of operation for this inverter. The voltage VAB is a square wave, right? So here we have inverter, and the output of this inverter is a square wave, so we can remove the inverter and put a voltage source, a square wave, a voltage source. Okay, here in the load side we have the resonant inductance and the resonant capacitance. Okay, and we have the load. Okay, and here is the current IR. Now here we have four modes of operations. The first mode of operation, when the input voltage is positive and the current is positive as well. So here we can put a positive DC input and the current is positive. Then the conduction will be at which switches? At switch 1 and 2, right? So we can say switch 1 is on and switch 2 is on. Let's call this mode number 1. Now mode number 2, the voltage is negative, but the current is positive. So the current will keep flowing in this direction, but the voltage can be negative. For this mode, the conduction will be through which diodes or which transistors? Diode 3 and diode 4. These two diodes will be conducting. Now for mode 3, the voltage is negative and the current is negative. So here switch 3 and switch 4 are conducting and the current is flowing in these two switches. Okay, because we said positive positive, switch 1 and 2, negative negative, switch 3 and 4. So here the input is positive but the current is negative, so the conduction will be through diode 1 and diode 2. So these are the four modes of operations, and we study these four modes of operations when we studied the inverter, if you remember. But now we record these ones because we will see at which mode of these operations we can operate the inverter to be a series resonant converter or a series resonant inverter. Now, if you look at this circuit again and try to draw the voltage VAB, this is T, this is VAB, the voltage, this is the voltage, and here is the current. Let's say the current is like this. This is inductive circuit. Why it's inductive? Because the current is delayed. When the current is delayed, we say that the inductor holds the current. When the inductor holds the current, this means we have inductive circuit. Now let's say the input voltage is like this and the current is like this. If we are not operating for the resonant converter, if the load is just a resistive load, so of course this is a resistive. But if we have two passive elements, capacitor, inductor, and resistor, this is a resonant circuit and the output is operating at resonance. Okay, and we expect that we are operating at the maximum power, at the maximum current. So this is a good point here. Also, you'll find that when we make switching here, when we apply switching action at these 2 points, if you remember, we said that here we apply signals on switch 1 and 2, and here we apply signal on switch 3 and 4. So the switching action occurs at zero current, zero voltage switching, soft switching. So that's why we can obtain, in addition to the maximum power that can be extracted, also when we apply switching action, this occurs at soft switching. So the voltage or the current can be zero, then we apply the switching action. Okay, we send the signal at this point. Now let's recall the impedance for this circuit for the series resonant inverter. So the impedance is equal to how much for the load? R plus J omega LR plus 1 over J omega CR, right? And again, the resonant frequency is equal to how much? 1 over LRCR, and F naught 1 over 2 pi LRCR. Here, I will say that omega S is equal to 2 pi times the switching frequency, and this is what? The switching frequency. Okay, this is switching frequency, and this is what? The resonant frequency. Now, the switching frequency and the resonant frequency are not always the same. If the switching frequency is equal to the resonant frequency, then at this point, yes, our inverter will work as a resonant circuit. Okay, but if the switching frequency is larger than the resonant frequency, then the converter will not be able to work as a resonant converter. Okay, it will be inductive, for example. Okay, inductive converter or inductive inverter. Now, when we talk about the equality factor here, Q is equal to how much? Omega naught LR over R. And remember, this is for the series resonant circuit. And this is 1 over omega naught CR times R, which is LR over CR over R. And this is what? The characteristic impedance over R, the equivalent resistive impedance over the resistance. Okay? Now, if you look at the quality factor, high quality factor means small r, right? Small r means what? High power, high current, or what we call heavy load. Small quality factors means what? High R, high resistive load, and also what? This means light load. Now let's draw the relation between the frequency, the normalized frequency, omega s over omega naught. Now from this figure we understand that omega s over omega naught, the resonance occur when omega s over omega naught is equal to 1. So this is 1, and this is again omega s over omega naught. And here we'll draw this one versus the impedance over R and the angle of the impedance. You'll find that for this series resonant inverter, the curve will look like this. If you try to draw the angle of this, it will be something like this. So the start will be narrower, and here it can be wider. Now this value here, Q value increases. Okay, when Q increases means we have what? We have narrower shape for the for Z over R. Okay, and here we have the same thing when Q increases. And here the maximum is how much? plus 90 degrees minus 90 degrees. Clear? Now let's try to find the value for the voltage VAB, the input voltage. The input voltage is equal to how much? VAB of T is equal to how much? Sum from n equals to 1 to, for many values, for odd values only, odd harmonics, okay, for VDC over n times pi sine n omega t. Now, if we have a square wave like this, and this square wave, the maximum is VDC plus VDC minus VDC. So this, we said this is a fundamental frequency, right? The fundamental sine wave plus third harmonic, fifth harmonic, and so on. Now, what is the value, what is the amplitude of this sine wave, the first harmonic? It's not VDC. VDC, this is for the square wave, but for the first harmonic is equal to how much? 4 VDC over pi. So this sine wave is usually a bit larger than the square wave, the first harmonic, which is 4 times 4 over 3.14 pi, right? So 4 VDC over pi, the maximum here. So again, if you have a square wave like this is VDC and minus VDC, the sine wave is larger than the amplitude of this sine wave is 4 VDC over pi. For the third harmonic is equal to how much? 4 VDC over pi times n times 3. For the fifth, 4 VDC over pi times 5, and so on and so forth. So this is the input voltage, VAB, the square value. Now for the output, V output is equal to how much? V out is equal to 4 VDC over n pi times R over Zn sine n omega t minus the angle of the impedance. Okay, and this is for n equals to 1 for the odd values. Now for the nth harmonic, V out is equal to how much? For the nth harmonic, 4 VDC over n pi times R over the impedance here, R squared plus n omega s LR minus 1 over n omega s, the switching frequency CR. So this is the output value for the nth harmonic. Try to make some simplification for this value. So you'll find that V output is equal to how much? The output voltage for the nth harmonic, for the first harmonic, for this third, and so on and so forth. Just try to revise this one here. VAB, the relation between VAB and V out. VAB is the input, and V out is what? Is the voltage on the resistor. Now what is the difference between these two? Tell me, how can we find the difference between these two? We have the input voltage, we have the output voltage, and we have impedance between them, right? Impedance. Like look at this here. This capacitor, inductor, and resistor. Right? This is V out and this is VAB. V out is equal to how much? Voltage divider. This over all impedance here times VAB, right? R over the whole impedance Zn times VAB, right? So that's how we obtain this one. Just voltage divider. V out over VAB is equal to how much? R over R plus the reactance of the capacitor and the inductor. R plus the reactance of the capacitor and inductor is the Zn. Now let's come back to this one. The output voltage V output VON, the nth harmonic, is equal to how much? We said this is n omega s LR, so we can simplify this one. This will be 4 VDC over n pi times R over R squared plus. Now we will try to make some simplification for n omega s times LR, right? N omega s times LR. Now LR from the quality factor is equal to how much? LR is equal to how much? R, the resistive value, times the quality factor over omega naught. Because LR, the resonant inductor, the resonant inductance, this is the only value that can be linked to the resonant frequency. Omega s is the switching frequency, not the resonant frequency. The inductor and the capacitor, LR and CR, the resonant capacitor, the resonant inductor, these can be linked to the resonant frequency. So we can say that n omega s times RQ over omega naught. Similarly, we can replace CR with here RQ omega naught over n omega s, and all of these squared. Now omega naught over omega s, here we have also omega s over omega naught. The quality factor can be taken out. Okay, so you can say that we have q squared out of this term, and then here we have n omega s over omega naught, and all r values will be taken out. So we have v out is equal to how much? 4 v dc over n pi times, now here is 1 because r will go with r, and here we have 1 plus q squared times n omega s over omega naught minus omega naught over n omega s, and this is squared. Since this is the input voltage value, right, for VDC over n pi, so the input voltage value is equal to this value, so we can say that V out n over V input n is equal to how much? 1 over 1 plus q squared, and this is n omega s over omega naught minus omega naught over n omega s squared. Okay, and this is the relation between the input voltage and the output voltage with respect to the quality factor and the resonant frequency. Now let's look at this equation. When omega s over omega naught is equal to 1, this means what? This means resonance frequency. Okay, so we're operating at resonance. So this will be 1, right? And this will be 1. And we can say this term is equal to how much? N minus 1 over n. If omega s over omega naught is equal to 1, so this is at resonance, and q is high, what happens? So we can say that V output 1 is equal to how much? 4 V dc over pi, and here the angle of z is equal to 0. Why? Because we operating at resonance. So this is for the first harmonic, because we said n over, again, if you come back to this equation, which is V out for the nth harmonic is equal to how much? 4 VDC over n pi times what? 1 plus q squared. Here we have n omega s over omega naught minus omega naught over n omega s squared, right? We said this is 1 and this is 1, and for the first harmonic, so this is how much? 1, and this is 1, so 1 minus 1 is 0. 0 times q, 0. 1 over 1 is 1, and this is 1. So here we left with what? 4 VDC over pi, which is the peak for the first harmonic. Okay, we agreed on this one. Now, for the third harmonic, omega s over omega naught is 1. So we can say that n minus 1 over n. So 3 minus 1 over 3 is how much? 2 plus something squared. It will be large value. And if the q we said is high, so this means we have what? We have a large value for n, like 2 squared, how much? Like let's say 9 or 8. 8 times a large value of q, let's say q is 10, so this is 100. 100 times 8 is 800, right? So V out the third harmonic, it will be how much? It will be very small. So here for the third harmonic, this value is equal to how much? 4 times V dc over 3 pi times, if you calculate it, you'll find it's 0.037. Very small value. And this is when q is 10. So we can simplify this and say V, the third harmonic, and the fifth harmonic is even smaller than this value, and the seventh harmonic and so on is equal to 0. That's why for resonant converters, if you select q is high, this will act as a filter. And this is clear from what we obtained here. The third harmonic is almost 0. So this is one good advantage in in resonant inverters. So we said this acts as a filter, right? So let's say this is the first harmonic. The third harmonic is here. It will be multiplied by 0, so it will not appear. So the output will be sine wave. V out is sine wave. That is a very good point. Now, if you look at the AB, the input voltage, it's a square wave like this. The output voltage, it will be a sine wave, okay, which is the first frequency only, the fundamental frequency V out 1. And also, this is not only V out 1, V out 1 plus all harmonics, but the whole harmonics, V out 3, 4, 5, and 7, all these are very small. We said they are very small, so they will not appear. And this is the current. If you look at the switch number 1, okay, you'll find that switch number 1 is 0 when it's conducting, because at this point we said switch 1 and switch 2 are conducting, okay, are on. And here switch 1 and switch 2 are off. When switch 1 is off, the voltage across switch 1 will be how much? VDC. And the current will be, of course, 0. And because we operate at resonance here, omega s over omega naught is equal to 1, so you'll find that this portion of current, I out, it will be exactly the current that is flowing within switch number 1. So when we apply switching action here, this will be soft switching. Here also we have soft switching. We have two modes only. Although we have capacitor and inductor, but we operate in mode 1 and mode 3. Okay, let's say, for example, if omega s over omega naught is not equal to 0 and Q is high as well, what happens at this moment? The fundamental frequency is equal to how much? V out 1 is equal to 4 VDC over pi times, let's say, K. Okay, because we have 1 over 1 plus Q times something. This is a value. It's not 1, right? This is a value. You'll find that this K is from, it's less than 1. Okay, it's not equal to 1, it's less than 1. And the angle here of the impedance will be equal to alpha. So here we operate, let's say, here at this point. Here is omega s over omega naught is equal to 1, but here we increased the frequency, so the amplitude is less than the maximum. So this is 4 VDC over pi times K, right? And K is less than 1. And we said we prefer to operate at higher switching frequency rather than operating here. By this we can control with the voltage, with the output voltage, right? Because if we increase the frequency, we can operate at different values for the voltage. If you don't care about the switch, about the frequency on the output, so we can simply make a voltage control here. Sometimes we can underload our inverter and operate at this point, for example, and whenever we need, we can go upper until we get the maximum power, okay, or the maximum voltage. So we can make voltage control here, voltage control. Now this is for the fundamental frequency. You'll find that the third frequency here, let's say this is the first, okay, the third will be even far away from the fundamental frequency. It will be even removed easier. So here, if you try to calculate the fundamental frequency, it will be V out 3, which is 4 VDC over 3 pi times 0.037 times K less than 1. So it will be even smaller than the previous one. And this at Q factor equals to 10. So we can simply say that the third, fifth, seventh, how much? 0. They are cancelled. Filter again, because the resonant converter, the load resonant converter, LR and CR can act as a filter. Now, because we said we increase the frequency on the right, like greater than the frequency, our frequency now is greater than the resonant frequency. This means what? This means we have inductive load, right? Inductive load means the current is delayed. Okay, as we can see here, the current is delayed. So we have inductive load here, inductive converter. The current is delayed from the voltage. But do we operate at resonance? Of course not. Okay, not resonance, it's inductive. If we try to calculate for switch 1, you will find that switch 1 voltage is equal to VDC when they are off and 0 volt when they are on. But here, if you look at this portion, this is the output current. It will be applied on this switch number 1. So this portion is coming here. Again, this portion here is coming here. So if you look at this current here, at this point, we have what we call hard switching. Hard switching. Why? Because this is a zero, not a zero current switching. We have hard switching because the current has value when we send the switching order. When we turn off the switch here, switch 1, and give order to switch 3 and 4, okay, to be conducting. So the current here was not zero. The current here is not zero, so we have like significant losses. What about the losses, the switching here at this point, here and here? This is soft switching for switch 1. Why? Because look at switch 1 here, switch 1 and 2, and here we are studying switch 1 only. Look at this point, switch 1 is on, nothing here, no problems. So at this point and this point we have hard switching, and here we have soft switching. Now let's go for one example here. The example says we have a 10 ohm resistive load, and this resistive load requires 1 kilohertz 50 volt RMS sinusoidal voltage to operate. So we have load. This load is a resistive load. This load can operate at 1 kilohertz and 50 volt RMS value. The question says design a series resonant inverter for this application so that the total harmonic distortion of the load voltage must be less than 5% and determine the maximum voltage across the capacitor. How to solve this question? Now, since we know the information for the load voltage, the amplitude of 50 volt RMS value is equal to how much? Sine wave is equal to 50 times the root square of 2, which is how much? 70.7 volt. If the RMS is 50 volt, then the peak is 70.7 volt for a sine wave. We know that the relation between the sine wave and the square wave, if this is VDC, this is how much? 4 over pi times VDC. So from this information, we can obtain the input voltage. So we can say that we know that V out is equal to how much? 4 VDC over pi. So from here, we can say that VDC is equal to how much? Pi over 4 times V out. From here, we can say that VDC is equal to 55.5 volt. Okay, we obtain the DC voltage. Why do we need the DC voltage? Because we need to design a series resonant converter, and we know that the relation between V out and V in. So now we know the input voltage value. We know the output voltage value, which is 70.7. We know the input voltage DC value, which is how much? 55.5. Now what other information we have? The question says we must design this inverter to make sure that the total harmonic distortion is less than 5%. So we can say that the total harmonic distortion by definition is equal to how much? The sum of the harmonics, which are not the fundamental harmonic, n is not equal to 1 squared over the first harmonic. Now we can simply ignore the fifth, seventh harmonic because they are definitely very small, equal to 0, and we can consider only the third harmonic. So we can say that this is equal to V3 over V1. Now when you go and design your inverter, you can say that V3 over V1 must be less than 0.05%, or if you want to make sure that your total harmonic distortion is definitely less than 5, you can say V3 over V1 is less than 4, for example, just to make sure that the fifth, seventh harmonic are considered. But here I will say V3 over V1 is less than 5%. And from this we can say that the third harmonic is equal to how much? Must be less than 0.05 times 70.7. Okay, the peak value for the fundamental frequency. And here V3 must be less than 3.535 volt. Now let's take this value, the third harmonic, okay, which is important now, and put it in our equation that we just obtained. So we can say that the third harmonic over the input voltage is equal to how much? 3.535 over 70.7 over 3. The n value is 3. So this will be equal to how much? 1 over 1 plus q squared 3 omega s over omega naught minus omega naught over 3 omega s, and this will be squared. Try to solve this equation. Here we operate at resonance. Okay, so you can say that this is 0.15 and this is 1 over 1 plus q squared 3 minus 1 over 3. Solve this equation, you'll find that we have 0.0225. This is equal to 1 over 1 plus 7.1 q squared. From this we can find the quality factor for our converter, because the factor that can determine the values of the capacitor and the inductor is what? Is the quality factor. So from this we can say that q is equal to how much? 2.47, and from the quality factor we can obtain the value of the inductor and the capacitor. So q is equal to how much? Omega naught times Lr over R, and from this equation Lr is equal to how much? 3.93 millihenry, and q is equal to how much? Here 1 over omega naught R CR, and this can bring what? The CR value, which is 6.44 microfarads. So here we obtain the values for the capacitor and the inductor, the resonant capacitor and the resonant inductor, and we have the resonant frequency, which is 1 kilohertz. So if we design this inverter with these values, the capacitor and the inductor, and 1 kilohertz switching frequency, so definitely this will obtain what? A resonant converter. Okay, the current and the voltage will be in phase. By this we obtained the values of the capacitor and inductors. We designed the inverter. The second part of the question says find the value of the voltage across the capacitor. Now this is very simple. We can say that VC is equal to how much? The current. The voltage is equal to I times R, and the voltage in the capacitor I times the impedance, the reactance. So this will be how much? J omega naught times CR. The current is how much? V1 over R over omega naught times CR. By this we can say that this is 70.7 over 10 over 2 pi times 1000 times 6.44 micro. The voltage here, how much? Is 175 volt. So this is the voltage across the capacitor. Now look at the voltage here. Now this is when the Q is how much? Is 2.47. If we try to increase the Q, okay, you'll find that the voltage stress, or the voltage across the capacitor, is larger. And note here, look at this voltage, 175. This value is greater than the input and the output voltage. So let's say, for example, your voltage on the output is 70 point something, or on the input is 50 point something, right? So for resonant converter, one of the problems in resonant converter is that, yes, we can cancel the effect of the capacitors and the inductors, but the voltage tolerance, or the voltage stress across these capacitors, across these elements, must be large to be able to handle the resonance effect. Okay, I'll stop here for today, and I'll see you next week.